recording. Share screen. Go full screen. Does it look okay? Good, good. All right, so let us get started. So the last time we talked about motivations, why you want to study quantum field theory. So that what we do today is to sort of basically review quantum mechanics. And to get started with the quantum mechanics, we use Lagrangian and Hamiltonian, which I believe you have studied in some class on classical mechanics. But just in case that you want to review it, there is a file in the miscellaneous folder on B courses that reviews the classical mechanics using Lagrangian and Hamiltonian. So yeah, you can actually review that. So anyway, so in most discussions, I actually start with the Lagrangian. And much of the things you probably studied in quantum mechanics class is starting from the Hamiltonian. So that's a little bit of difference here, but you quickly get used to that idea. So what do you know from about Lagrangian, I believe, is that Lagrangian gives you an action, and the variational principle of the action gives you the Euler-Lagrange equation, which is nothing but the Newtonian equations of motion. But in addition, what's important in quantum theory is that Lagrangian also determines the canonical structure, namely that for a coordinate in the Lagrangian, x, you define p, that's a canonical momentum. And once you're given a Lagrangian, there's a unique way of identifying what should be p for a given x. So that's something that turns out to be quite important for the rest of the discussion here. And Lagrangian is useful for to capture symmetries of the system. And the reason is that the in Lorentz invariant theories, once you try to incorporate relativity, you need to treat space and time on equal footing, right? But in the case of a Hamiltonian, it treats time differently from space. And so if you think about the Schrödinger equation, for example, Hamiltonian operator acting on the wave function is the time derivative of the wave function, right? That's what Schrödinger equation says. So Hamiltonian singles out time. So if you use Hamiltonian formulation, then it treats time and space differently. While if you use Lagrangian, then you can treat them on equal footing. So that's why we tend to prefer starting with the Lagrangian, not Hamiltonian. But of course, once you have a Lagrangian, you can derive Hamiltonian. Once you have a Hamiltonian, you can derive Lagrangian, so they're in one-to-one correspondence. So there's nothing gets lost by using Hamiltonian. But it just is more convenient to start with the Lagrangian for the purpose of incorporating relativity later on. And just in case that you're wondering about this spelling of Lagrangian, this is something I learned from Wikipedia. So apparently, the Mr. Lagrange was a Italian, Giuseppe Luigi Lagrangia, but he eventually naturalized to France and became Joseph Louis Lagrange. So we talk about Lagrange, but Lagrangian with I goes back to the original spelling, Italian spelling of his name. So that's why we don't put E here, but instead I, apparently. So that's something I got very confused when I was back in grad school. So this is something it may be useful to know. Just a little story behind the guy. Mr. Lagrange was Italian and hence Lagrangian. All right, so the Lagrangian, as I said, is something that's supposed to give you the action of the system. And as you, I believe, all know, action is a time integral of the Lagrangian. And Lagrangian is supposed to be a function of canonical coordinate qi and its time derivative. And for the canonical formulation, it doesn't contain double time derivative, third time derivative, and so on. It stops with the first order time derivative. So it's a function of q and q dot. And therefore, if you differentiate Lagrangian with respect to q dot, the time derivative of the coordinate, that defines the canonical conjugate momentum. And then you define Hamiltonian, which is pq dot minus L. And here you have to actually do a little bit of work because using this definition of P, you want to eliminate Q dot in favor of P in the expression of Lagrangian, which is a function of Q and Q dot. So you'd like to eliminate this Q dot in favor of P. And also here, you eliminate this Q dot in favor of P so that the Hamiltonian is a function of P and Q. So it should not contain time derivative in it. And so, and then once you have this Hamiltonian, then you go to the quantum theory by imposing this canonical quantization condition or canonical commutation relation. QP is given by IH bar. And if you have many Qs in a system, then each Q comes with its own P, and Q and P satisfies this canonical commutation relation for each pair of Q and P. And that's something you all used in the quantum mechanics class. And here's just one example of a harmonic oscillator. So here I have many x's, but only one omega for the harmonic oscillator. So this is actually a spherically symmetric harmonic oscillator in some number of dimensions. And for each xi, that's the canonical coordinate qi, I define pi by taking the derivative of the Lagrangian with respect to xi dot. And it's easy to see that's m times xi dot. So that's the canonical momentum conjugate to xi. And of course, you are very familiar with this expression. Momentum is m mass times the velocity. So that's the canonically conjugate momentum for this Lagrangian. And then you define the Hamiltonian as px dot minus L. But as I emphasized, you are supposed to eliminate x dot in favor of P. So whenever you see x dot, you rewrite it in terms of P over M. So here I have Px dot, but I eliminate this x dot by P over M. And do the same thing here. So Lxx dot, which is the original Lagrangian up here, which is written down here exactly the way it is, except that I eliminate x dot in favor of P over M. So this is Px dot minus L, but now it's written as a function of x and P. And the first term in the square bracket partially cancels this Px dot piece, and that becomes P squared over 2m. And potential energy comes with a minus sign in the Lagrangian. But because this Hamiltonian is Px dot minus L, the potential energy now flipped sign to become the positive sign. And this is the potential in harmonic oscillator, half m omega squared x squared. So that's something you have seen, I'm sure, many times. And so this is the way you write the Hamiltonian as a function of x and p after eliminating x dot in favor of p. And in harmonic oscillator, because p is mx dot, now I know what p is. And then you set up this canonical commutation relation between x and p, which is IH bar delta ij. So that's the standard formulation, starting with a Hamiltonian Lagrangian. So in this case, half mx dot squared minus half m omega x squared, that's the Lagrangian. And then from the Lagrangian, you define canonically conjugate momentum. You derive Hamiltonian. And once you know what the canonical conjugate momentum is, you set up this canonical commutation relation to quantize the system. So writing down the Hamiltonian can be done within the classical mechanics. So up to this point, this is same as the classical mechanics. But when you set up this canonical commutation relation, you have H bar in it. And that's where quantum mechanics starts. So that's just a quick review of using Lagrangian and Hamiltonian to get started in looking at some quantum system. Okay, let me stop here once and see if there are any questions about this. Everything okay? All right, so as I said, if you go to B courses and under files, you see a folder, miscellaneous, MISC, and in that folder, you see a file classical1.pdf. And that's a lecture note I had written a while ago when I was teaching graduate level quantum mechanics 221, just again for the purpose of reviewing classical mechanics. But what you study in undergraduate classes is the same level for that purpose. So that's, I think, will be helpful if you haven't actually looked at Lagrangian Hamiltonian recently. Just refresh your memory about this. Okay, so once you have derived Hamiltonian and canonical commutation relation, then we can work out the Schrödinger equation. So in this abstract Ket-Bra notation Dirac introduced, you define a state using a Ket, which is a function of time, and time derivative times IH bar of that Ket. So this tells you how this state would evolve in time. And that time derivative is given by acting Hamiltonian operator on this Ket. So Hamiltonian is now written as a function of Q and P. Now both Q and P are operators in quantum mechanics. And so acting this Hamiltonian operator on the Ket psi is what tells you how the state evolves in time. So that's what you learn in quantum mechanics class. And now that you have this canonical commutation relation between X and P operators, you can go to the position space where this Q bra is an eigenbra of the operator Q. And because of this canonical commutation relation, if you are on this space where Q is diagonal, momentum operator can be written as a derivative with respect to Q. So P written as H over I del Q is what satisfies this canonical commutation relation. So that's how we know when you are in this space where Q is diagonal, then the momentum operator can be written as a derivative with respect to Q. So that's what we know for this coordinate representation of the Hilbert space. So using this Q bra and taking the inner product of Q bra with this state psi, you define this wave function, which is a function of Q, which is the eigenvalue of the Q operator, and time. And time is what determines the time evolution of the state psi, right? So this is the definition of the wave function. And because this wave function is given in terms of Q psi inner product, and the time dependence is only in psi, Q is time independent here. The time derivative of the wave function has time derivative acting only on psi because Q bra is time independent. And the idea of the Schrödinger equation is that time derivative of the state is given in terms of the Hamiltonian operator acting on the state. I get the second line over here. And the Hamiltonian is a function of Q and P. And Q operator acting on Q bra just pulls out the eigenvalue Q. So now this Q is a number instead of an operator. On the other hand, P operator here acting on this Q bra is given by this Q derivative. So this Hamiltonian operator then can be written as a differential operator acting on this inner product Q and psi, which is nothing but this wave function. So this is how you understand the Schrödinger equation. So Schrödinger equation is meant to be this abstract equation, how this ket evolves as a function of time by using the Hamiltonian operator. But for most practical purposes, we switch to this coordinate representation and use this wave function as a function of Q. Now this is actually a function, so there's no operator involved in here. Then you find this differential equation on this wave function psi of Q and T once you know this Hamiltonian, and that's how you actually write down the standard Schrödinger equation. And once again, by specializing this to the example of harmonic oscillator, we derive this Hamiltonian operator on the previous slide, which was written as p squared over 2m plus half m omega squared x squared. So at this stage, x is an operator, p is also an operator. And now you define this Schrödinger wave function, which is the function of x and t. So in this expression, x is no longer an operator. It's an eigenvalue of x operator. So it's a number x. And using this formulation down here, time derivative of the wave function psi of x and t for the harmonic oscillator is given by this differential operator acting on this wave function psi of x and t. And because p acting in this coordinate representation is given by this del x times h over I, so 1 over 2m is here, h bar over I twice is h bar squared, then minus sign, and you have two derivatives with respect to x. And this potential energy term, this x is an operator in the Hamiltonian, but this operator now turns into the eigenvalue x. So this is x is now a number, or C number. So hence we derive this Schrödinger equation, which is the simple differential equation with respect to x and t. So that's how you get the Schrödinger equation. So one thing I'm sure you learned in quantum mechanics class, but let me emphasize just once again, Hamiltonian in the Schrödinger equation has the meaning of something that moves time forward. And given that Hamiltonian is time independent, at least in the case of this harmonic oscillator, this is time independent. Time derivative gives you Hamiltonian. Therefore, I can write a abstract solution, symbolic solution to the Schrödinger equation that psi evolves in time according to the unitary operator, which is just exponential of the Hamiltonian in the exponent times minus it over h bar. So it's easy to check that once you write this psi of t in an abstract fashion using this unitary operator e to the minus iht over h bar acting on the state at the initial time 0, you can check easily that taking time derivative, you basically pull out everything in the exponent because it has time in it. So you pull out minus I h over h bar. And having I h bar here cancels minus I and over h bar. So that leaves only h up front. And h acting on this whole thing using this equation is psi of t itself. So that recovers this equation, h operator acting on ket psi of t. So this is what I mean by Hamiltonian moves time forward. Namely that once you know what the Hamiltonian operator is, that dictates how the state evolves in time by using this exponential of the Hamiltonian operator. Because Hamiltonian is Hermitian, this e to the minus I ht over h bar is a unitary operator. And unitarity, as you know, is important in quantum mechanics because unitarity is what guarantees the probability is conserved. Namely, that if you take the norm of the state after time evolution, because this operator in yellow is unitary, this cancels when you take the norm because you bring in Hermitian conjugate on this side. Hermitian conjugate of the unitary operator is its inverse. So if I call this operator u, u dagger times u is 1. And therefore, this operator actually cancels when you take absolute squared. So psi t absolute squared remains the same as psi 0 absolute squared. And absolute squared of the ket is the probability. Therefore, probability is conserved in time evolution. So that's the important thing in quantum mechanics. So this is again just a review. But the point here is that Schrödinger equation is what dictates time evolution of a state, which can be formally integrated by using this unitary operator e to the minus I ht over h bar. And because the time evolution is given by this unitary operator, it conserves the probability. So that's how we actually use the Schrödinger equation to solve some explicit problems like a harmonic oscillator. And as you know, and we actually come to that in a moment, the Schrödinger equation for harmonic oscillator can be solved explicitly using Hermite polynomials, but we can also solve the same problem of the harmonic oscillator and work out eigenvalues in a totally algebraic fashion using these abstract x and p operators. And I will go ahead and review that in a moment. So you can do it either way. Because using these operators and using this coordinate representation is in one-to-one correspondence, is totally equivalent. You can switch one from the other and go back and forth. So solving Schrödinger equation as a differential equation in x and t and try to understand the eigenvalue problem of the Hamiltonian using operators is exactly the same thing. And of course, you find the same answers. For example, what the eigenvalues are for the Hamiltonian in harmonic oscillator, you can do it either way using differential equation like this one, or using the p and x operators in an algebraic fashion. So we use both formulations and switch back and forth. Okay, so this is again the review, very quick review of the quantum mechanics. Are there any questions about this? So you're all comfortable with this, it looks like. Very good. I see some of you nodding, which is great. Visual feedback is very, very helpful, so I really appreciate it. Okay, so this e to the minus iht over h bar, because of the discussion we just had, is called time evolution operator. And therefore, Hamiltonian operator is what gives you infinitesimal time evolution. And this unitary operator is the finite time evolution over the finite interval t. So once again, h gives you infinitesimal time evolution. What's meant by this is that that's the time derivative. And if you integrate this, you find this unitary operator for the finite duration time evolution, and that's this e to the minus iht over h bar. So this is what is called the time evolution operator. And again, this is something you have done a lot in quantum mechanics class. So once you have this Schrödinger equation, you look for eigenstates of the Hamiltonian operator. So eigenstate of Hamiltonian operator is defined by this equation, namely that Hamiltonian operator acting on ket gives you an eigenvalue E. So that's the definition of an eigenstate. So once you have an eigenstate psi, then this time evolution equation, IH bar DDT psi, is now given by this eigenvalue E. And then you know exactly how to solve this equation, namely that the state changes only by a phase, e to the minus iet over h bar. So this is what is called the stationary states, because once you have a state whose phase changes by time, but nothing else, then state basically remains the same, because the phase would drop out whenever you compute something that has to do with the probability. So in some sense, this oval phase doesn't really matter. So the state psi practically remains the same independent of time. And that's the meaning of the stationary state. So this state psi is basically remains the same no matter how long you watch the system. So that's the meaning of the stationary states. And again, going back to the example of harmonic oscillator, you know the eigenstate equation. So again, you look for the eigenstate of Hamiltonian operator of H. And you, of course, know the eigenvalues as well. We come back to that. And that's H bar omega times n plus 1 half. So you know the eigenvalues. And so you then solve this Schrödinger equation in coordinate space, which is this ordinary differential equation with respect to x, because time derivative part is now given by this eigenvalue E. So that's the equation you want to solve. And you find these general solutions given in terms of Hermite polynomials. And so that's something you study in quantum mechanics class. Hermite polynomials is one of those special functions, and they are orthogonal polynomials using this weight, e to the minus m omega x squared over 2h bar. So the psi for different eigenvalue E are orthogonal to each other. And the eigenvalues, as you all know, is given by this h bar omega times half odd integers n plus 1 half. So again, this is what you have seen in quantum mechanics class, and this is how you would solve it using this coordinate space differential equation. And then on next slide, I switch over to another way using operators. I'm sure you have seen that as well. But anyway, so this is the way you can solve the problem of the harmonic oscillator. Okay, any questions about this? Again, this is just a review, but if anything is unclear, don't hesitate to ask me. No questions are dumb. I always emphasize that. By the way, I really like questions because when I was teaching a grad level QFT course several years ago, there was a one student who kept asking lots of questions to the extent that I was sometimes a little annoyed. But because he has so many questions, one of the questions he asked turned out to be something I didn't know the answer to. So we decided to get together and start working on that question. And we ended up writing 7 papers together. So you never know. So if you ask a good question, that might actually turn out to be a research problem. And we might end up like writing a paper together. So, the questions actually very productive in that sense. And also that if you ask questions, even if you think it might be a dumb question, that might end up helping your fellow students who are shy not to ask the question himself or herself. But if you ask the question, that gets clarified. So he or she would appreciate that. So as I always say, no questions are dumb. Asking questions is actually being productive and helpful. So that's why I encourage questions. But anyway, so any questions at this stage?
Can you please go over again why psi is equal to psi of 0 times the time evolution piece? I just forget where that comes
Yeah,
from.
yeah, yeah. No, thank you for asking the question. So the from Schrödinger equation, IH by ddt of ket is given by the Hamiltonian operator acting on psi. But for an eigenstate of the Hamiltonian operator is just replaced by a number e. So you have this differential equation that time derivative gives you a number. So that's something you can solve. That's the ordinary differential equation. And here is the solution. So by taking time derivative that acts on this exponent, that pulls out minus IE of h bar from the time derivative out of this exponential factor. And IH bar up front cancels minus I and 1 over h bar, so that this turns out to be just E. So you can explicitly verify that this phase factor is the solution to this differential equation. So that's how we know this is the
Okay,
solution.
thank you.
Good. Thanks for the question. Any other
Mhm.
questions?
Okay.
Great. And actually, I don't see your name. Natalie, is that right?
Yeah, Natalie.
Okay. Thank you, Natalie. All right. So this is how you solve the problem of the eigen problem of the Hamiltonian operator. And as you all know, the eigenvalue of the Hamiltonian operator is the energy of the state. That's why I'm using this symbol capital E. So that's the review of the formulation. So starting with the Lagrangian, you define canonically conjugate momentum P that allows you to set up the canonical commutation relation that ends up giving you the Hilbert space. And also, once you have the Lagrangian, you can derive the Hamiltonian. And Hamiltonian is this infinitesimal time evolution operator. So that's why you can write down the Schrödinger equation. And Schrödinger equation dictates the time evolution of the state. And once you solve the Schrödinger equation, you know how a given state would evolve as a function of time. And once you solve that differential equation, then you have solved the problem of the dynamics of the system. So once you're given Lagrangian, the rest follows. And in some cases, you can solve the problem. In many cases, you do not solve the problem exactly. You have to rely on some approximation methods like perturbation theory. But in whatever the case you're looking at, once you have Lagrangian, then you know exactly what the system is. And in principle, you can solve the problem completely to understand the dynamics of the system. So that's the basic idea of starting with the classical Lagrangian and find the solutions in the quantum system. So harmonic oscillator is the prime example where you can really solve the problem. And there's an alternative formulation without relying on these Hermite polynomials. Just by looking at the X and P operators and switching over to creation annihilation operators. So that's the thing I'd like to review now. And so this is actually a very beautiful way of solving the harmonic oscillator problem, thanks to Dirac. By the way, actually, I didn't know till recently that he actually moved from UK to Florida State University towards his latter part of his life. And I was invited to be the Dirac lecturer at the Florida State University last semester. So that's when I learned that, okay, so Dirac had something to do with the Florida State University. So he eventually died there, and his tomb is also in Florida. So that was something I didn't know before, and I learned it. So it was a big honor to be named the Dirac lecturer, obviously, and it was a lot of fun to talk about various aspects of quantum physics and cosmology and particle physics. Anyway, so thanks to Dirac, we have this alternative way of solving the problem of harmonic oscillator. So we have derived this harmonic oscillator Hamiltonian as a function of P and X operators. And so classically, if you look at something which is given by square of one thing plus square of another thing, you can immediately write it as a combination of, so if this is a squared plus b squared, I can write it as a minus ib times a plus ib that recovers a squared plus b squared. So classically, I can take this form of the harmonic oscillator, which is a sum of square of x and p, and write it in terms of basically x minus ip times x plus ip. And there are these cumbersome factors here using m and omega, but nonetheless, this is something you can do. But we have to remember that x and p are not numbers anymore, they are operators. So I have to be a little bit careful about the ordering between x and p. For example, if I look at the cross term in this expression, this times that has p in front of x. On the other hand, this times that have x in front of p. So they come with the opposite ordering between x and p. So that's why I have to be a little bit more careful about this. So at the classical level, this is completely okay. But now that we are talking about quantum mechanics, it's not okay. I have to be a little bit more careful. So once I try to be careful, then there's this extra term here, which is half h bar omega. So that's why we have this half h bar omega in the energy levels of the Hamiltonian in quantum theory. So paying a little bit more careful attention to h bar here, we define a dagger operator, which is the first factor in the square root, except for this h bar factor. So this thing here over square root of h bar is a dagger. And same thing for the second thing in parentheses. Again, this thing in parentheses over square root of h bar is what we define as an a operator. So this thing is therefore square root of h bar times a dagger. Second parenthesis is square root of h bar times a. So then I can write the Hamiltonian as h bar omega a dagger a plus 1/2. So that's the expression you often see in quantum mechanics textbook. And you can also derive the commutation relation between A and A dagger operators because you know X's commute, P's commute, but X and P satisfy this canonical commutation relation. XP commutator is IH bar. So using this, you can work out A and A dagger commutator. And A has this X in it times the square root of M omega over 2H bar. A dagger has P in it times this I over 2mH bar omega. So using this canonical commutation relation, you can work that out. And then you find 1/2 from that. Another contribution is P in A times minus I over 2H omega H bar omega square root. And A dagger has this X in it times this coefficient of square root M omega over 2H bar. So that gives you yet another contribution to this A dagger commutator of 1/2. So they add up to 1. So once you have this A written this way and A dagger written that way, A in A dagger commutator is 1, while the Hamiltonian is now written in a much simpler form of H bar omega, is a number, times A dagger A operator plus 1/2. So that's something you have seen again in quantum mechanics class. But anyway, so I'm reviewing that. Any questions about this? And all of these things about harmonic oscillator is reviewed in the lecture notes on B courses, harmonicoscillator.pdf. So if you have anything that's not clear to you, then I hope you will look at the lecture notes and get and really get everything clarified. So the reason I'm talking about harmonic oscillator right now is for two different reasons. One of them is just a great way of remembering and just reviewing this algebraic method in quantum mechanics. So this is a review. But it turns out that we also use harmonic oscillator a lot when we go to quantum field theory. So right now we are doing quantum mechanics, but when you go to quantum field theory, we use this actually a lot. So that's why I want to make sure that you are completely familiar and comfortable with this algebraic method in harmonic oscillator. Okay, so once again, if there are any questions, please fire up.
What was the reason that this method came later than the previous method you showed? Is that correct that it came afterwards?
Yeah, that's right. So Schrödinger worked out the Schrödinger equation, and you might have heard a little bit about the history of this. Before Schrödinger, Heisenberg had a different formulation of quantum mechanics called matrix mechanics. So Heisenberg wrote X and P as a huge matrices, and that's something, of course, you know how to do now. Once you have Ketten-Bra notation, you can write X as a matrix in the Hamiltonian eigenstates, and P also as a big matrix. Both of them are infinite dimensional matrix. So the initial formulation by Heisenberg was using those matrices. But completely independently, Schrödinger came up with the differential equation in coordinate space, which is nothing but the Schrödinger equation. So you had two different formulations, which seems to give you the same answer. And that was actually a big puzzle. So then came Dirac. So he basically unified this matrix mechanics by Heisenberg and Schrödinger equation derived by Schrödinger into the same single formulation using this abstract Bra and Ket. And that's where this idea of the algebraic formulation came out. So Schrödinger did this, Heisenberg did matrices, but in the end, according to Dirac, both of them turned out to be the same thing just by looking at these operators. So using operator written as a matrix in the energy eigenstate turns out to be Heisenberg's matrix mechanics. On the other hand, writing down differential equation in coordinate space turns out to be the Schrödinger equation. So out of the same abstract formation using this algebra and Hilbert space gives you both Heisenberg's matrix mechanics and Schrödinger equation, and you can derive both of them from this formulation. So this is how Dirac unified Heisenberg formulation and Schrödinger's formulation. So this is actually what Dirac got the Nobel Prize for. Thank you for asking that question. Any other questions here? Everything okay? All right, so let me then move forward. So we introduced this A, which is called annihilation operator, and A dagger, which is called the creation operator. And once you have this annihilation creation operator, which satisfies this canonical commutation relation, and Hamiltonian, which is now written using this annihilation and creation operator, you know how you can solve the eigenvalue problem of the Hamiltonian. So you first define the ground state. And one thing you know is that this Hamiltonian is given in terms of A dagger A, which is a positive semi-definite operator, because A times Hermitian conjugate of A is always positive semi-definite. So that's something you can prove this way. So if you sandwich Hamiltonian operator in arbitrary state psi, which is given by this ket, and its Hermitian conjugate bra, then you can use this expression to write it as a sum of two terms. The second term is just a number. So whatever this ket psi is, as long as it's normalized to unity, it just gives you this number half h bar omega. So second piece is just a number. The first piece has this operator in it, so that's where you have to think a little bit. But given that A dagger is a Hermitian conjugate of A, this expectation value of A dagger A can be written as a norm of the state A acting on ket psi, because A acting on ket psi is the second half of this matrix element, but norm has this Hermitian conjugate to it. So when you take Hermitian conjugate of A acting on psi, psi ket turns into psi bra, A turns into A dagger. So this norm of A psi turns out to be exactly this expectation value of A dagger A operator in the ket psi. So the first term of the Hamiltonian is now cast into a norm of the state A acting on psi times this coefficient h bar omega. And what we know from linear algebra is that whenever you have a norm of a vector, that's positive semi-definite. So the smallest it can be is 0. So here's now an inequality that Hamiltonian expectation value is larger than or equal to the number half h bar omega, because this first piece is positive semi-definite. It is positive or 0, can never be negative, because it's an absolute square of a vector in this Hilbert space. So that's the smallest what the expectation value of the Hamiltonian operator can be. So in order to have the lowest energy, that's the definition of the ground state, you want to have this A acting on psi ket to be 0. So that's the definition of the ground state. Namely that when you find a state which is annihilated by this annihilation operator A, that is the state with the minimum energy, and therefore that is the ground state. And now knowing this definition of this annihilation operator A, then you can solve this equation, what this ground state would look like in the coordinate space. So what we know is that annihilation operator acting on the ground state returns 0. And when you take the coordinate representation of this equation here, you put in this coordinate bra, so that's an eigenstate of the x operator. So this x here is a number, And A has this X operator in it. So I hope there's no confusion here. This X is an operator. This X is a number as an eigenvalue of X. So this X operator turns into X eigenvalue X number. And P operator, as we talked about 2 slides ago, is a derivative with respect to X. So this equation that A annihilates the ground state can be now written as this differential equation with respect to X. So I'm looking for a function where derivative with respect to X returns X. And that's a simple differential equation you can solve right away, namely that it has the form given by this Gaussian function. So because Gaussian has x squared in exponent, and taking x derivative, that would bring x down from the exponent. So derivative of x squared, of course, is 2x times m omega over 2h bar gives you m omega over h bar. It cancels this factor over half because x squared derivative is 2x. So that's you can see that this function satisfies this differential equation for the ground state. So that's how you can work out the ground state wave function. So the beauty of this is that, I have no memory of how Hermite polynomials look like. I don't remember that. And of course, I can rely on Mathematica to actually get the explicit expression out of it, but certainly I don't remember it. So if I want to solve the harmonic oscillator problem when I'm actually on a train or bus or airplane, and I don't remember polynomials, but using the annihilation and creation operator, I can work out the wave function of the ground state. Uh, no, no, I don't have to remember anything. So this is how you obtain the ground state wave function. And ground state wave function is determined from this condition that it is annihilated by this annihilation operator. So when you act Hamiltonian operator on the ground state, the first term has A now acting on the ground state, that gives you 0. So A dagger A is 0 on the ground state. And that's how you know that ground state has energy eigenvalue half times h bar omega. And we have proven that's the smallest the energy can be using this semi-positive definiteness of the norm of the vector in Hilbert space. So that's how you can obtain the ground state wave function for the harmonic oscillator. And what is useful here is this combination of A dagger times A. That is what we call the number operator. And given that A annihilates the ground state, number operator acting on the ground state is 0. And that's why we call this ground state as 0 ket, where this 0 is referring to the eigenvalue of this number operator n. So that's how we know how to solve the harmonic oscillator ground state. So ground state is given by this condition that it gets annihilated by the annihilation operator. Then you know immediately that Hamiltonian eigenvalue on the ground state is half h bar omega because the first term gives you 0, given that it is an eigenstate of this number operator with a 0 eigenvalue. And once you know that this is what defines the ground state, you can immediately write down the wave function for the ground state as well by solving this simple first order differential equation in X. And second order differential equation for the harmonic oscillator is complicated. Sorry, I wanted to go back even further. So this is the second order differential equation with respect to X. And I don't remember how to solve this equation in general. And so that's why I have to look up some textbook and get told that it's given by this Hermite polynomial times this Gaussian factor. I certainly don't remember that. But when you actually go to this algebraic method by Dirac, then I can just straight go to this first order differential equation on the ground state wave function. And this first order differential equation is something I know how to solve, which turns out to be just simple Gaussian. So the beauty of this is, once again, I don't need to remember anything about special functions, orthogonal polynomials, all that stuff. I can just immediately jump into this condition that the ground state is annihilated by this annihilation operator, and then that tells you exactly what the wave function looks like up to an overall normalization factor n. And of course, you can just simply do a Gaussian integral to determine what this normalization factor is also easily as well. So only thing you need to remember is how to do a Gaussian integral to derive correctly normalized eigenfunction of the Hamiltonian for the ground state. So that's really the beauty of Dirac's method. You don't need to remember anything. You just go through this idea of looking for the lowest energy state, which is determined by this semi-definiteness of the vectors in Hilbert space. And that gives you this condition for the ground state, namely it's annihilated by the annihilation operator. That gives you the first order differential equation. Then you find the wave function. So that's how you know what the ground state of a harmonic oscillator is. Okay, so now it's getting a little bit more technical. So I'm sure you got some questions here. Don't hesitate to ask. I see something on chat. Is this just for the case of the harmonic oscillator? So what is this here? What is the question again, Andy?
Great.
Yeah.
Oh,
Can you hear me?
I can hear you.
Okay. So all that we've calculated here is that just specific to the harmonic oscillator, Hamiltonian?
So the way the Hamiltonian can be written as annihilation operator times creation operator is specific to the harmonic oscillator. That
Okay.
idea of this positive semi-definiteness is true no matter what Hamiltonian is. But here I'm relying on the fact that this annihilation operator is what gives you the Hamiltonian, which is specific to the harmonic oscillator. That's why I can change the problem of solving for the ground state to another problem of looking for a state that gets annihilated by the annihilation operator. So this condition is specific to the harmonic oscillator.
Okay. Thank you.
Is that what we need to know? Okay, good. Thank you for asking the
Yes.
question, Andy. Any other questions here?
Yeah, I have a quick question.
Go ahead, Adi.
When you're looking for the state that gets annihilated by the annihilation operator, do you
Mhm.
only know it exists once you explicitly solve the differential equation, or do you know it exists beforehand?
I would say we know that exists beforehand, but looking at the function is something we are more familiar with rather than the abstract Hilbert space. By solving for it, we get sort of reassured that, okay, this state does exist. So we don't have to do this. We can rely on just this algebraic equation in the abstract Hilbert space. But this just gives you a little bit more familiar language to get reassured that such a state does exist. So that's my view on this problem. Is that a good answer, Adi?
Yeah, thanks.
Okay. Any other questions at this stage?
So from just what you have up on the slide, is it immediately obvious that A is an annihilation operator, or are you already coming in with that knowledge that it decreases the energy level and A dagger increases the energy level?
So far, we don't know that yet. So the only thing we know at this stage is that when you look for the ground state of the harmonic oscillator, that is the same problem as looking at this equation, that you're looking for a state that gets annihilated by this annihilation operator. So that's the only thing we have done so far. And looking for this raising and lowering is something that appears, I believe, on the next slide.
Okay.
Okay.
But how do we know beforehand that A is supposed to annihilate?
Yeah, so at this stage, it's just the name. So I named this basically the square root of Hamiltonian as the annihilation operator. So at this point, this is just a name. So never mind, it has name annihilation in it. It's just the name for this operator A. And this operator A turns out to be useful because solving for the ground state turns out to be the same problem as looking for a state that gets annihilated by this operator.
I see. Thank you.
But of course,
Um,
annihilation operator turns out to have a good name, a good meaning for its name, because it really does turn out to be lowering operator of the excited state of Hamiltonian that comes up on the later slides. So
Right,
the
thank
name
you.
sort of anticipates the use of this
Yeah.
operator for the later purposes. Okay, any other questions?
Uh, yeah, so
Go ahead.
just to hop off that question, aren't you sort of assuming here that A has a non-trivial kernel? Because you're assuming that there's a non-zero state labeled by the eigenvalue 0, right?
So that's why confirming that point using explicit wave function was reassuring. So you might say that there's no guarantee that this operator does have a state which it can annihilate. But by explicitly solving this equation and finding an explicit wave function, you get reassured that such a state does exist. Does that make sense, Chirag?
Yep, thank you.
Okay, good. Any
Wait,
further
so you
questions?
do?
Go ahead.
Yeah, sorry. So you do need to solve the differential equation to know it exists. You don't know it exists beforehand?
No, I would say we basically are confident that this solution exists in an abstract way using this operator, but this is just a way of proving that it indeed does. Okay, are you happy, Adi?
How do you, sorry, I just want to make sure, how do you know it exists beforehand without solving the equation?
Okay, so is there a way of showing that this solution exists without switching to the wave function? That's the question you're asking.
Yeah.
Then I don't know the answer top of my head. I need to think about it. Of course, after the fact, we know. But your question is, how do we know this equation has a solution in abstract Hilbert space without switching to a particular representation? And then I don't know how to prove that right now. So let me think about it. If I find a solution to that problem, I will get back to you. Sorry.
No worries. Yeah, of course. Thanks.
That's a good question. I appreciate that. Any other questions?
Yeah, I have a question. So all of this was done just to find the wave function of the ground state of a harmonic oscillator.
Right.
That's correct? And so that's just what the last line is? Okay.
You in a car or something?
I'm on the tennis team here at Cal, and we're driving down right now to play UCLA tomorrow. So yeah,
wow.
so I'm in a bus. Yeah,
I see.
So,
okay.
So I'm in a bus. Yeah.
Okay. Good luck with your game.
Yeah. Thank you. Thanks.
Wow. Power of technology. Good. And any other questions?
Yeah.
Okay.
Sort of a minor detail, but when you pull the A operator outside of the bracket, the X goes from an operator to a number. How do we get the derivative with respect to X out?
Yeah. So that's where you relied on this canonical commutation relation. So the idea here is that X operator and P operator satisfy this canonical commutation relation. And this Q bra is an eigenstate of Q operator. So if you actually use this canonical commutation relation right next to this bra, when you have QP, the Q operator turns into number Q, and you have P operator acting on it. When you have the second term is commutated, that's negative PQ, you have P acting on Q bra, and you still have Q operator next to it. So you need to find a way of writing P operator in this Q representation. And once you identify this P operator acting on Q bra to be this differential operator, then you can confirm that you correctly reproduce this canonical commutation relation. So the idea of this quantization by Dirac is that this canonical quantization is given. Once you have a Lagrangian, you derive P, you set up this canonical commutation relation. And once you have this canonical commutation relation, you know that P is given in terms of this derivative operator with respect to Q to make sure this canonical commutation relation is satisfied in the space where Q is diagonal, namely Q is given by this eigenvalue. So canonical commutation relation is the important thing derived from Lagrangian. That's given. And once you're given the canonical commutation relation, you know what happens in the Q representation of the Hilbert space, where P operator is given by Q derivative and Q operator is given by number Q, to make sure that canonical commutation relation is reproduced. So that's the idea. Does that answer your question, Asha?
Yeah.
Great.
Thank you.
Okay. Because I intentionally made these animations to slow myself down, it does take a while to get back to the previous slide. Sorry about that. Okay, so now we have creation annihilation operator, harmonic oscillator, and then we have the ground state. And I see some posts on chat window. Oh yeah, good. Everybody's trying, hope for the success for Jacob. Good. I like this kind of camaraderie. Okay, and then we talk about excited states, right? So now we know what the ground state is, which is a state annihilated by the annihilation operator A. And the Hamiltonian is now written using this number operator, capital N. This is still an operator, not an eigenvalue. So we need to figure out what the eigenvalue of this N operator is. And of course, you know the answer, that turns to be just integer N, but we need to derive that. And once again, this commutation relation is the key. So using this commutation relation, I can work out the commutator between the number operator and the annihilation operator. So N is A dagger A is here, and A commute, so I can take this A out of this commutator to the right-hand side of the commutator. And then I have this A dagger left inside the commutator. A dagger A commutator is the negative of A dagger commutator. So that's -1. And I have A on the right-hand side of this commutator that's still there. So that's how we can derive NA commutator to be -A. We can do the same thing for N A dagger commutator. So N, once again, is defined to be A dagger A. And so this is A dagger A and A dagger commutator. A dagger commutes with A dagger. So this A dagger in A dagger A can be pulled out from the commutator to the left. Then I'm left with A dagger commutator. And that's something we know is +1. So that's how I end up getting plus A dagger. So N A dagger commutator is plus A dagger, and A commutator is -A. So this is done, again, purely algebraically. So if you think of n eigenstate with the eigenvalue n, at this point, we don't know yet that this n has to be integer. So this is a little bit misleading, maybe. We don't know this in an integer yet, but I'm using a symbol which is common for integers. But this is just the eigenvalue of this number operator, capital N, at this stage. And then you know, when you actually look at the state A acting on this n ket, you can show that the eigenvalue of n operator decreases by 1. So the point is that when you act this number operator n on this state an, I have na now acting on this ket n, and I can rewrite n times a as na minus an plus an. So an cancels between the two. So I didn't change anything. This whole thing in parentheses is still the same thing as NA. But the reason I'm writing this way is because this is useful. NA commutator is something I worked out, minus A. And this capital N acting directly on n ket just pulls out the eigenvalue little n. So I can put these things together as n minus 1 times A acting on this n ket. So the end result is that if n ket is an eigenstate of number operator n with the eigenvalue n, annihilation operator acting on this n ket is also an eigenstate of number operator capital N, but the eigenvalue now decreased by 1 to n minus 1. So that's something you learn from this. And another thing we know is that an ket is a vector in a Hilbert space, so its norm has to be positive semi-definite. And norm can be computed by the definition of ket n. So if I take absolute square of an, you have A acting on n, then you need a Hermitian conjugate of that. So n Hermitian conjugate is n bra, A Hermitian conjugate is A dagger, and given that this is an n operator itself, it just pulls out the eigenvalue n. So this n then has to be positive semi-definite. And given that this A operator decreases the eigenvalue to n minus 1, I can write this state as a ket n minus 1, but I need to also care about the normalization of the state. And what we computed here is basically the norm of the state an, and the norm is n. So if I want this n minus 1 ket to be correctly normalized, then you need to supply this normalization factor of square root of n. So what we learned here is that once you have this eigenstate of the number operator n with the eigenvalue little n, then an annihilation operator acting on this state n gives you another eigenstate of the number operator n minus 1 up to this normalization factor of square root n. So that's something we learned here, namely that I can use this annihilation operator to go down in the eigenvalue of this number operator n. Again, this is something you know from quantum mechanics class, but I'm deriving that, again, purely algebraically, namely that what we have learned that number operator n has this kind of commutation relation relying on the initial commutation relation of A and A dagger operators. That's the only thing you need to know. Once you have this definition of number operator, you can derive this commutation relation. And that then tells you that eigenstates of this number operator can be lowered by this annihilation operator up to this normalization factor square root n. Any questions here? Everything okay? Okay, so I can stop again once I finish this slide. So the opposite thing you can do is to act creation operator on this number state little n. Again, using this commutation relation, you can show that this A dagger acting on n is an eigenstate of the number operator with the eigenvalue n plus 1. So this is how you know A dagger would go up in the eigenvalue of the number operator. And once again, we need to make sure that we get correct normalization. And you do the same thing here. So norm of the state A dagger acting on number state n is given by A dagger acting on n and its Hermitian conjugate. N ket becomes n bra. A dagger dagger is A. So that's the thing you need to compute. And A dagger, using this commutation relation, is A dagger A plus 1 And a dagger a returns this eigenvalue little n, and plus 1 is still here. So that's how you know the norm of this state. So I can write a dagger n as the state n plus 1 together with its normalization factor given by square root of n plus 1. So now I learned that how I go up and down in the eigenvalues of n using annihilation operator and the creation operator. So any questions about this? Okay, then I also learned something important. So far, I didn't assume that the eigenvalue of a number operator has to be an integer. So in principle, it could have been any real number. But I also learned that using this A operator, I can keep making the eigenvalue of n operators smaller by 1, 2, 3, and so on and so forth. On the other hand, n operator is A dagger A, therefore n operator is positive semi-definite. You can never have an eigenvalue of n that's negative. So if there were a state, n ket, where n is not an integer, then I can keep acting A operator on top of it, and eventually I can go from n minus 1, n minus 2, dot, 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 and go to a point that the eigenvalue of n operator is negative. That's a contradiction because n operator is supposed to be positive semi-definite. To avoid that contradiction, I have to make sure that if I keep lowering n by acting A operator multiple times, before n gets negative, state itself has to vanish. The only way I can satisfy that condition is when n is integer. Because when I have n as an integer, let's say 1, if I lower the state by acting annihilation operator, I get 1 minus 1 as a norm, and then it vanishes, and you can't go any further. Maybe I misspoke. So if we have state 0, then by acting A on top of the state 0, then the normalization factor is square root of 0. So there's no state minus 1. So this is the way you can guarantee that operator n remains positive semi-definite as long as the eigenvalue of n operator is integers only. So if you have n as an integer, you can again keep lowering the eigenvalue n by acting annihilation operator. But when you get to 0 state, that's what we discussed in the previous slide, you cannot lower it any further. So then there's no concern about number operator n going negative, and therefore stays positive semi-definite. So when you write down this eigenvalue equation of this n operator, we didn't know ahead of the time that the eigenvalue has to be integer. But to be consistent with the semi-definiteness of this number operator n, we now learned that the eigenvalue has to be positive integer or 0. It cannot be negative integer. So this is the way we learn that the eigenvalue of this number operator n is a non-negative integer. And that's something you know, again, from quantum mechanics class, but that's the way you derive this eigenvalue problem of this n operator, which has to be a non-negative integer. Okay, that's a little technical discussion, but any questions about this? I'm sure there are.
Can you also verify it's an integer just by raising the ground state, because the ground state has an eigenvalue of 0?
Mm-hmm. Right. So this notation is consistent in a way that we defined ncat to be a state annihilated by the annihilation operator, but that also turns out to be zero eigenvalue state of the number operator. So that's why we call the state zero ket. So it's consistent that way. The notation is the good notation. Okay, any other questions? All right, so that's how you build the Hilbert space now. So a dagger acting on n ket gives you ket n plus 1 up to this normalization factor. So if you act a dagger on this n ket, you get n plus 1 state together with this normalization factor. And the same thing happens everywhere. So if you go back all the way to state 0, then you learn you can keep acting a dagger on top of it to go to state n, where you get this normalization factor square root n from 1 to n. So they all multiply together to give you n factorial inside the square root. So then you know what exactly this n ket is. So once you know this ground state, you just multiply a dagger operator n times to obtain this n ket up to the normalization factor of square root n factorial. So now you know what this n ket is. And we have solved the problem of what the wave function looks like for the ground state 0. We know a dagger is a differential operator in a position space. So then you can derive what the n ket wave function is without knowing anything about Hermite polynomial. At the same time, we learned that A acting on n gives you state n minus 1. So A state would keep lowering this state, eventually get down to this ground state 0. And then you cannot go any further because A acting on 0, as we just discussed on the previous slide, gives you normalization at 0. So there is no state minus 1 to worry about. So that's the way the Hilbert space works for the harmonic oscillator. And again, you have seen this before, but this is the way we derive everything from the purely algebraic point of view. And as I said, we end up actually using this a lot when we go to quantum field theory. Any questions? No? Okay. And it is also useful to write the Lagrangian using this annihilation and creation operator. So we start with the Lagrangian given by this half mx dot squared minus half m omega squared x squared, and derive the Hamiltonian as px dot minus L. Now I can use this backwards. We know a dagger and A expressed in terms of x and p. So by using this Hamiltonian backwards, I can write the Lagrangian as px dot minus h. And I know how to write p in terms of A and A dagger. So that's the imaginary part of A. So A minus A dagger gives you P up to some normalization factor. And and the X dot, X is given by the real part of A, namely A plus A dagger cancels the piece P. So up to some normalization factor, that gives you X dot. And we know the Hamiltonian given by A dagger A. So this is how you can write Lagrangian in terms of A and A dagger. And now I have a piece, A dot, which is the total derivative of A squared. And I'm sure you learned in classical mechanics class that the total derivative in the Lagrangian is something, it doesn't do anything for you, so you can drop it. A dagger times A dagger dot is also total derivative of A dagger squared. So that's something I can drop. So the piece I need to keep is A dagger times A dot. That's here. That's a half of it. Another piece I need to keep is A times A dagger dot. But because I'm allowed to drop total derivative, I can do integration by parts to let this time derivative on A dagger act on A instead. That gives me the same term, that's the other half, so that the entire first term is now reduced to IH bar A dagger A dot times A total derivative. Hamiltonian is minus H bar omega A dagger A, and 1/2 is just a constant, and constant is also a total derivative of T. So now I obtain the Lagrangian written in terms of annihilation and creation operator. And you probably haven't seen this before, but this is how the Lagrangian can be written using annihilation and creation operator. And this form is actually very useful because the first term tells you that A dagger derivative of the Lagrangian is nothing but A dagger times IH bar. So the canonical commutation relation immediately tells you that A dagger commutator is 1. So this first term gives you the commutation relation we used on the previous slide a lot. So this commutation relation in the first discussion came from XP commutation relation. But then I don't need to know anything about X and P anymore. I can just go straight to A and A dagger because now the Lagrangian is written using A and A dagger. And that Lagrangian tells you right away that A dagger commutator is indeed 1 because A and A dagger are canonically conjugate to each other up to this normalization factor of IH bar. Sorry, it's taking time. And now time is up. So let me finish very soon. So now that I've written the Lagrangian using A and A dagger, then you can derive this canonical commutation relation right away from this. So this is the way you can write everything in terms of A and A dagger without ever going back to X and P anymore. Okay, I stop here and I take questions, and then we start from where we left off. And the next thing we like to talk about is actually how we can recover classical motion of a harmonic oscillator using this quantum theory of using the Hilbert space. Okay, any questions here?
How do you,
Andy?
What is A dot signifying? Like
A dot,
it's
so dot is the Newton's notation for the time derivative. I'm sorry I didn't mention
okay.
that. Any other questions? Thank you, Andy, for clarifying questions. Any other questions?
Could you go over again how you get the commutator relation when you have an A dot? Because
right.
like how do you handle that?
Right. So we got A to be the coordinate in the Lagrangian. Then the derivative of the Lagrangian with respect to time derivative of the coordinate is what gives you the canonically conjugate momentum. So then you identify IH bar A dagger as the canonically conjugate momentum to A. Then the commutation relation is A IH bar A dagger commutator is IH bar. So I cancel IH bar from the both sides, and then I obtain A dagger commutator is 1. So this turns out to be a very useful way of writing Lagrangian, which gives you this A dagger commutator right away. Is that good, Chirag?
Yeah, that clarified. Thanks.
Okay, any other questions? Okay, so if you have any further questions, you can post the questions on Piazza or send me email. And you are welcome to consult the lecture notes on harmonicoscillator.pdf on all of this stuff. And then I post the homework problem, first homework problem today, and that is about a harmonic oscillator. And it would involve some problem on the coherent state that comes up actually on next Wednesday. So you can read ahead on the lecture note and start working on the problem, or you can wait till Wednesday when you actually hear about the coherent state and start working on the problem. But either way, I'm sure you can finish it by the next Friday. So that's the plan. And I see something on chat. Thanks, Professor. You're welcome. Okay, so have a good weekend, and I see you on Wednesday.
Thank you.
Then don't forget to fill out the doodle poll for the office hour. Only half of you have done that so far. So I really need everybody's participation on that. Okay?
Where is the poll posted, Professor?
I'm sorry?
Where is the poll posted?
So I actually made an announcement. So you must have received an email. And if you go to B courses, you can look up the announcement email as well. Or if you go to the slides from the Wednesday's lecture, the doodle poll is a link embedded into PDF.
Okay, thank you.
Okay. Anything else?
Thanks, Professor. See you next week.
Okay. Have a good weekend.